Today we learned this idea of the derivative. And just to kind of make sure we're all starting a little bit on the same page, when I say derivative, what should be kind of screaming in your head, like the concept of what the derivative represents?
The slope.
The slope. And specifically, it is the slope of the tangent line. But if you just get in your head, derivative is slope, that's going to be a good connection to have right now. So did want to review some notation. So yesterday we were just talking about the derivative and I wasn't really clear, like I have now this thing called the first derivative that you can see on the screen. Well, technically we can just like keep taking derivatives. So when I just say the derivative, I'm implying I'm talking about the first derivative, and we know some of the notation I use for the first derivative. We can use the f prime notation, or we can write that as dy dx. Or the Newton notation, but it's not really important for us. Well, there's also things called the second derivative, which is literally the derivative of the first derivative. How we represent the second derivative is in prime notation. You just write it with two primes next to it. You literally read that out loud as f double prime. The second derivative in the dy dx notation looks a little bit funny, but it looks like this. Those look like exponents. I don't ever read that any differently. When I see that symbol, I just say, hey, that's the second derivative. It's just the easiest way to explain it. Those two symbols are interchangeable. We'll be using the prime notation more often for this first part of the class, just because it's simpler to use and not as awkward to write down. But technically you can like keep taking derivatives. There's like a third derivative, a fourth derivative, fifth derivative, sixth derivative, so on and so on. Some of them have fun names. I mean, maybe fun to other people, but like the third derivative, its mathematical name is literally called a jerk. So if someone ever calls you a jerk, you can call them a third derivative back, and then they just probably will call you a nerd. But we have first derivative and second derivative, and that's what we're going to focus on today. And so what I want you to be able to follow along with in your notes is this chart. Again, we will refer to this chart so frequently, like you will memorize it pretty quickly. But it is something that you will want to use to kind of help you until you learn and have it all memorized. So how I have the chart set up is I have 4 columns. The first column is going to be what the graph looks like. And then I have a column for f, f prime, and f double prime. And we're just going to talk about like, hey, when the first derivative is this is some possibilities of what the graph could look like. Or if the second derivative is this is what the graph could kind of look like. These first 4 rows deal with just some like, not really calculus stuff, but just some ideas of what the graph looks like. So if I just talk about f of a, and I say that this y value, f of a, is positive, where do we know that this graph has to be located at if I say f of a is positive?
Above the x-axis?
Above the x-axis. So we just know that somewhere we are above the x-axis. And you can kind of follow through. If I say that f of a is negative, we know that we are below the x-axis. If I say f of a is 0, then that means we are on the x-axis. And then if I just say that f of a is not defined, we know that that can mean several different things. We know that we could have some sort of discontinuity. And of course, those discontinuities could possibly be a jump. It might be a hole, or it might be a vertical asymptote. We don't know if I just give you that information. The only thing we know for certain is that f of a is not defined. The rest of the rows for that one, we're not really going to fill in. For example, if I just say, hey, this graph is above the x-axis, we don't really know anything else about it without more information. So if you are just provided information about where the graph is located, I'm just going to put like lines through it. Like we won't ever really talk about what the first derivative is doing unless we can see more of the graph. This thing called the second derivative, we're not really going to think about what it's doing on the graph either. We do have some other phrases I'm going to introduce. So if the f of a is not defined, then you also can't have a derivative there. So f prime of a is not defined. And then likewise, if you don't have a function there, you don't have a first derivative there, well, guess what? You're also not going to have a second derivative there. So f double prime of a is not defined. So that row of the chart is not really that exciting. Like there's no calculus there. That's just kind of where the graph is located at. Where the calculus is going to come into play is starting with the next 4 sets of rows. And that's when we see f prime is positive, negative, 0, and then not defined. So let's review from yesterday. If I say that f prime of a is positive, what does that mean in terms of your graph of a? If f prime is positive, what's the graph doing?
It's increasing.
It's increasing. And so we're going to say f is increasing at a. And it is important, and we are going to emphasize this a lot. When I say something is positive, that's not going to be the same as saying something is necessarily increasing. So we're going to keep those words kind of separated. So if you're kind of looking at the phrasing of this, we have f prime is positive means f, the function, is increasing. Well, you might not have thought too much about it before, but there's 3 ways a graph can increase in math. You can have a graph that increases linearly, like it could be steeper or flatter, but it can increase in a straight line. You can have a graph that increases and kind of bends upward, like an exponential. Or you can have a graph that increases and kind of bends the other way, like maybe a square root function or a log function. But those are really the only 3 ways that a graph could increase. Like you can change the steepness of it, but either it's going to be flat, it's going to bend one way, or it's going to bend the other way. And that's true when we talk about the other parts here. So if f prime of a is negative, we know that that means f is decreasing at this value of a. A graph can decrease in 3 ways. It can be a straight line and decrease. It can bend upward and decrease, or it can bend downward and decrease. All 3 of those are examples of the graph decreasing. And then we have f prime of a is equal to 0. What do we say was happening on the graph if f prime of a was 0?
It's a horizontal asymptote.
There's a horizontal tangent on f. So f has a horizontal tangent. And that can also look different ways. So you could have a horizontal tangent if the graph is just flat and horizontal, like the whole thing is a horizontal tangent itself. You might have something like a quadratic. Whether it's facing up or down, you have a horizontal tangent where it changes direction. You can also have a horizontal tangent in between the function, where it might be flat for an instant and then be increasing or decreasing. But without any information, we don't know what's happening around that value, but we just know at that value, there is going to be a horizontal tangent. And then we talked about the different cases of when we had a derivative that was not defined. What was one of the cases where a derivative would not be defined?
Approaching infinity.
So this is a derivative, not a limit. So when we had 3 cases where a derivative, I might have said it wrong, where a derivative is not defined.
The corners.
The cusp.
So we have a corner or a cusp.
Oh,
So remember, that's when you have a sharp turn in the graph. What else would be a case where you have no derivative?
a hole.
A hole, and really any discontinuity would be a place where you have no derivative. And then the other one is when you have a vertical tangent, because if you know the graph is going vertical, then we say the slope is undefined there. I'm going to introduce a new phrase to you right now. Another way of saying, hey, this function f doesn't have a derivative is we'll say the phrase f is not differentiable. at the x equal a value. So when I say differentiable, that just means, hey, this has a derivative, it has a slope. So if I say it's not differentiable, we're basically saying that it doesn't have a slope at that location. And similar to that chart above it, if I just know a graph is increasing or decreasing, I don't know anything about this thing called the second derivative. So we're going to leave this third column for that one blank. But if you're looking at this chart, super important to kind of know and interpret what it means if f prime is positive, negative, or zero, and then the possibilities of what the graph could look like. Someone was about to ask a question. What was it?
Yeah, could you just repeat that last part? You kind of broke up a little bit.
The last part, I mean, the most important thing from those graphs is understanding, like if I say f prime is positive, you know the graph is increasing.
Okay, awesome, thank you.
So now these last 4 rows, this is going to be really, I think, the new part for today. And this is going to be what the second derivative tells us. So everything above that might be either a review or not too new to you. These rows will be new. And so the first derivative is associated with whether a graph is increasing or decreasing. A second derivative is going to be associated with something called the concavity of a graph. I think of the concavity of the way of how a graph is bending. So the ways that we're going to think about this, if f prime is, excuse me, let me try again. If f double prime is positive, so this is the second derivative. When the second derivative is positive, then f is concave up at A. So we have concave up at A. And when I say concave up, you can abbreviate that. We'll often just abbreviate it as CC up arrow, concave up. A graph that is concave up to me always looks like a bowl. So it's going to be something that can hold water. So an example of a concave up function might be something that's increasing in concave up, something that's decreasing from concave up, or you can have a graph that decreases and increases, but is still concave up. But a concave up function is going to have some sort of bowl shape to it. And so then you can probably make some other assumptions. What do you think it's going to mean if the second derivative is negative?
Concave down.
So we have f is concave down. When I think about concave down, we can abbreviate it CC down arrow. Concave down graphs to me always going to look like a part of an umbrella. So it can be increasing in concave down, decreasing in concave down, or it can be increasing and decreasing in concave down. And then I'm going to fill in these boxes. I'm going to put them in a blue box because these are commonly messed up when I'm about to put in these 2 rows, and I'll explain in a second why it is the way it is. So I mentioned earlier we want to make sure we're careful with being distinguished with what we mean by saying positive or increasing, like those 2 words mean different things. And what I mean by that, so when I say f double prime is positive, that does mean that f is concave up. But what does that mean about f prime? And that means that if f double prime is positive, f prime is increasing. Likewise, if f double prime is negative, that means that f prime is decreasing. And this is where students often, like, until they get used to it, have some misunderstandings. So if I say f prime is negative, that's not the same thing as saying f prime is decreasing. For example, in math, you can have things that are decreasing and negative, but you can also have things that are decreasing and positive. So we are going to want to keep those things kind of separated. I'll go into the next slide to kind of show you in a second why we mean like what it means. But this also kind of means everything in that row is equivalent. So if I just tell you, hey, f prime is increasing, I want you to also know, hey, that means that the second derivative is positive, and that also means that the original function is concave up. Those three statements in that row are interchangeable. Likewise, if I say f prime is decreasing, that means the function is concave up, and that means that the second derivative is less than 0. For these bottom two rows, they aren't as interesting. I'm going to fill them in so you have a full chart. But if I'm looking at that very last row first, I'm going to fill in. If I have f double prime of a is not defined, then that just means that f prime of a is not differentiable. So basically, if we can't have a second derivative, then that means the first derivative probably was not differentiable. And if there's no second derivative, then the original function is not twice differentiable, meaning you can't take the derivative of it twice. But it's not really an interesting thing on the graph. Like, I'm going to kind of leave it blank because there's lots of different things that could be happening there. We just aren't quite sure without more information. This row above it, we are going to fill in some things. So if I tell you that f double prime is equal to 0, this means that f prime has a horizontal tangent. And for the other parts, I don't want to give us too much at one point, but I'm going to call this for f. I'm going to put a question mark here for now until we get some more math behind us. But I am going to put also a question mark there. So we won't really talk a lot about that second derivative until unit 3. There are some weird things that can happen when the second derivative is 0, but what's most important are those two rows above it, where we're saying that f prime is increasing and f prime is decreasing. Any questions on that chart before I look at just the two examples I want to get done today?
Can you explain the not twice differential again?
Yeah, so when I say not twice differentiable, that just means, so like the word differentiable means you can take the derivative. It has a slope. So if I say not twice differentiable, we're literally saying, hey, there is not a second derivative. Like if I said something like is not thrice differentiable, you would say like it wouldn't have a third derivative. We won't really take it that far, but just twice differentiable means I can normally take the derivative twice. So if it's not twice differentiable, it just means I can't take the derivative twice. And we don't really know what the graph looks like.
Thank you.
So the two examples, and this is what your homework looks like. You actually have just one page of these. Is I give you two sets of information before we start doing a little bit more with this. And I give you two statements, and I want you to draw a possible graph that would match those statements. So looking at example A, I have f of a is greater than 0 and f prime of a is less than 0. So if I want to draw a possible graph, well, if I see f of a is greater than 0, what is that going to mean about my graph?
Positive?
Positive, so we just know that the graph needs to be above the x-axis. We don't know where, we just need to make sure that it's above the x-axis somewhere. And then my second statement here, I have f prime is less than 0. If f prime is less than 0, what do I also know about the graph at A?
It's decreasing.
It's decreasing. So I just want to draw a graph that is above the x-axis and decreasing at A. So an example would be, there's a graph that works. If I want to be more clear, I'll keep it completely above the x-axis. So we could draw a linear graph. Do I know anything about the concavity just based off of that description? Or do I know anything about the second derivative based off of that description only?
No.
No.
No, so like you could have drawn it concave down, or you could have drawn it concave up. But based off of that description, that's the only way you could have drawn those graphs. Looking at this second one, let's see if we can draw a graph that matches. So I have f prime is increasing at x. That's pretty clear of what it looks like. And then I see that this f double prime is less than 0. So I know that it is increasing the graph, and I have f double prime is less than 0. If I say f double prime is less than 0, what does that mean in the context of what your graph is going to look like?
Concave down.
Concave down. So concave down. Concave down, remember, is going to be like an umbrella shape. So I want to draw an increasing graph that looks like part of an umbrella. It doesn't say whether it's above or below the x-axis, so it doesn't matter. So I'm going to just draw an increasing function that looks like an umbrella. Notice I wouldn't want to draw it going this way or straight up because those would not have a concavity that matches what's being asked for. I do want to say that there are lots of different ways we could have written this question. For example, I could have written B as this statement, f prime of x is greater than 0 and f prime is decreasing. That statement I just wrote down means exactly the same thing as what was typed in originally. So we know that an equivalent statement of saying that f is increasing, I could have just said f prime is greater than 0. Also, an equivalent statement of saying that f double prime is less than 0, I could have said f prime is decreasing. Those phrases are interchangeable. We want to get kind of used to being able to switch between those two and interpreting them as both meaning, hey, the original function is concave down. Questions on those two graphs or anything? Mitchell, you have your hand up.
Yeah. So the graph has to pass through the dotted line, right? The A.
We just know, yeah, at A, it needs to be increasing and concave down. So I do often have students confused. They're like, all right, Mr. Brown, I don't understand how if f is, in this case, like f is decreasing, how that means the graph is also like itself increasing. So this, I don't know, sometimes it confuses people more than others, but I do want to kind of give you a reason of certain things. So if I say f prime is increasing, we know that that is the same thing as saying, in this case, f double prime is greater than 0, which is the same thing as saying that the graph of f is concave up. Like all three of those statements mean the same thing. So like I have a generic number line here, and if I say f prime is increasing, like I can just pick any random number and just start increasing those numbers. And so literally what that means, if I say f prime is increasing, that means that my slopes are getting bigger and bigger and bigger. They are increasing in value. So we start off with having like a steep negative slope, and then it kind of changes from there. So when I go to graph it, we have like a slope of -2, a slope of 1, a slope of 0, a slope of 2, a slope of 3, a slope of 4. And you can kind of see that as the slopes increase, the graph does end up having this concave up bend. So that's kind of the theory about why it works. If you're like, Mr. Brown, I have no idea what you just did, then I'm going to be like, that's fine. I just want you to make sure we memorize this chart and understand the relationships we have in this chart. Particularly the bottom kind of 2/3 of it when you're talking about the first derivative and the second derivative. So your homework tonight, it should be another short one. But at this point, you do have the ability to do homeworks number 1 and homeworks number 2. Both of those have been distributed out to you via OneNote. The next topic we're doing is going to be a little bit longer. We're actually going to spend 3 days on the next topic, and then you actually will have 3 days of review before the quiz. So I'm trying to get a lot of the notes done earlier so that we can kind of space out the review and do what we need to do. So at this point, I'm going to go ahead and end class. If you are good to go, then you're welcome to leave, and I'll see you tomorrow. If you want to hang back and ask any questions, the recording will be stopped, and you can hang back